Hello, ladies and gentlemen, and we've got some videos here for you. We're going to do, this video will be on exponential growth, and then I'll do another video on exponential decay. So we did a little bit of work today on what our exponential functions look like, and we talked a little bit about their overall shape. And right now we'll do a bit of an exercise that sort of gives us some data to work with and to take a look at how this might come about. So, an exponential function occurs frequently in nature and society. It can be used in problems such as population growth, compound interest, investment growth, bacterial growth, and radioactive decay. We spent a good deal of time in class talking about different examples of that, and that was a lot of fun and interesting for us. Example 1. A type of bacteria grows so that it triples in number every day. So let's stop and think about that. So it's going to triple in number every day. So our first day will have however many, and then after a complete day goes by, you'll have 3 times that amount. After another day goes by, you'll have 3 times that amount. After another day goes by, you'll have 3 times that amount. So the base of this exponential function is going to be 3, and it's going to be an exponential growth function. Roger is growing a culture of these bacteria. He begins with an initial population of 100 bacterium. A. Find the population after each of the first 4 days. Well, he's starting off with 100 bacteria. Now, I can't say that this is day 1, because what this is talking about is after a complete day has gone by. So I need to come up with this idea of when time starts. So we're going to say 0. And so what we're going to say is that this is the initial start time. Okay, so time equals 0. After 1 day, so after 1 day's gone by, you're going to have 300, 3 times that amount. After 2 days, you'll have 900. After 3 days, you'll have 2,700. And after 4 days, you'll have 8,100 bacteria. Okay, so we can take a look at this. And it says, use finite differences to prove that the bacterium grows at an exponential rate. Well, once again, this part of the information is going to come down here. So at 0 was 100 again. That's at the beginning of, let's call it an experiment, if you will. It's at the very beginning of this situation. Time equals 0. As soon as when time is 0, we have 100 bacteria. As soon as we let time start ticking away, once we get to 1 day in duration, then we've got 300 bacterium. 2 days, 900 bacterium. 3 days, 2,700 bacterium. 4 days, 8,100 bacterium. Now, let's think about our first differences. Well, what you do is we're going to take our population of 300 and it subtract 100, so it's going to give you 200. You're going to have 900, subtract 300, so it's going to be 600. You're going to need 2,700 minus 900, and that's going to give you, I'm not good with this, I think that's going to give us 1,800. That makes sense. I better get a calculator. And you lousy kids keep borrowing my calculators. There we go. And now I'm going to have 8,100, subtract 2,700, 8,100, subtract 2,700, and I get 5,400. I better check this one. 2,700, subtract 900. It was 1,800. Okay, so there's good. So notice that your first differences are not constant. What does that mean? It means that it's not linear. Therefore, not linear. That's all that means. Now let's go into our second finite differences. Let's make the chart look a little bit pretty. And I'll just draw a line down here for our second finite differences. So what's going to happen now for our second finite differences, we're going to take a look at 600 minus 200, which is 400. 1,800 minus 600, which is 1,200. 5,400 minus 1,800 is 3,600. So your second finite differences are not constant. What does that mean? It means that this is not a quadratic. So, our conclusion is that it's not linear and it's not quadratic. Unfortunately, that's a pretty lousy conclusion. I think we can do better than this if we know a little bit more. And what we need to know a little bit more is that this function is actually not going to have a first finite differences being constant because it's not linear. It's not going to have a second finite differences that are constant because it's not quadratic. But it does have something. It has what's called the ratio of the differences is constant. Now let's take a look at what that looks like. So if I take 600 and divide, well, we can go back to the first finite differences. We can look at 300 divided by 100, and that'll give us 3. We can look at 900 divided by 300, and that'll give us 3. We can look at 2,700 divided by 900, and that'll give us 3. We can look at 8,100 divided by 2,700, and that'll give us 3. So this is your ratio of your differences, and they're all 3. Notice we could have done the same thing here. The ratio between 600 and 2, so 600 divided by 200 is 3. 1,800 divided by 600 is 3. 5,400 divided by 1,800 is 3. Same would happen here. 1,200 divided by 400 is 3. 3,600 divided by 1,200 is 3. So that ratio is staying constant, not only all the way down here between the first finite differences, but also between the second finite differences and also between our y values. So when you see that, what you have is, our conclusion is going to be that this is an exponential growth. Okay, this is an exponential growth function, which means that you're always going to be going up by a constant ratio. So you're not always going to be going up by the same amount. You're going to be going up by a ratio of the same amount. So each time we seem to be multiplying, if we go back to our original equation, we're multiplying by 3. 3 times as much. 3 times as much. 3 times as much. 3 times as much. And that makes sense. If you go back to the question, it says that it's tripling. So that's our tripling power in there. So now it's going to ask us for an equation. I'd like an equation to model the growth of this bacteria. So you could say that the population equals however much you start with, 100, and then it's going to triple for every number of days. Now, if we wanted to be a little bit more mathematical in our notation, we should say that the population in terms of the variable x is going to be equal to 100 tripling time in x, where x is the number of days. So there's a formula that'll model this growth. Assuming this trend continues, predict the population after 1 week and after 2 weeks. Now notice that this is in weeks. We have an equation that's modeling in terms of days. So the population there for the first week would actually be 7 days. So that's going to be 100 times 3 to the 7. So using our calculator, so it's 3 to the exponent 7 equals times 100, and I get 218,700 bacterium. After 2 weeks is the next question. So the population after 14 days is 100 times 3 to the 14. Now remember your order of operations here, guys. We got to do this first. You can't be taking the 100 in. So on my calculator, it's 3 to the exponent 14, I hit equals, times 100. And I get a really big number, and it looks like 478,296,900 bacterium. So look at the jump here. In just 7 more days, we've got this many more bacterium compared to that many more. And how did we get it? By tripling this number for another 7 days after we got to this point. All right, so I'm going to take a look at what's on the back here. And it looks like that we have another example, but this is going to be for half-life. So taking a look at this, example 2, one isotope of uranium, U-239, decays or changes into a new substance called plutonium-239. This highly toxic waste material has a half-life of 24 years. Okay, so that's pretty important. We know that the half-life is 24 years. Now what that means is that this substance will decay to half of its mass in 24 years. So when 24 years go by, only half of it will be remaining. After another 24 years, only half of that will be remaining. After another 24 years, only half of that will be remaining. Now remember, it doesn't matter how big of amount you start with. If I start with a bucket full, after 24 years, I have half a bucket. If I start with a truck full, after 24 years, I have half a truck full. It doesn't matter how much. Now, neat thing about radioactive decay, I hope that you understand, is what happens is you have a matter, you have a substance, and it's giving off energy. That energy is what we call radioactive energy. And what happens is, to give off energy, this needs to give up something, and it gives up mass. And so as the energy comes off, the substance is losing mass, and that's the relationship between the two of them. So let's take a look at the work here. Find the decay of 50 milligrams of this substance using the following table. So we're going to start off with 50 milligrams. That's how much we started. A neat way of using that is to say the initial amount. Notice our time in years is in 0. After one half-life, well, the half-life is going to be 24 years. After 2 half-lives, it's going to be 48 years. 3 half-lives, well, that'll be 72 years, and then finally 96 years. Let's just make sure I did that right. So 24 plus 24, 48 plus another 24, 72 plus another 24, 96. All right. What's happening to the amount of substance that we have, though? Well, it's halving each time we hit a half-life, or in 24-year intervals. So we go down to 25 milligrams. Then we go down to 12.5 milligrams. Then we go down to 6.25 milligrams. And then we go down to 3.125, I think. Let me check. 6.25 divided by 2 is going to be 3.125. I am correct. And that's what we have happening there. So, kind of interesting. Let's transfer that information down to here. So at the initial time, we've got 0 years have gone by. It's right when it's starting. You're starting with 50 milligrams. After 24 years, 25 milligrams. After 48, 72, 96, we're going to have, let me just hit the focus here. I'm not sure if I'm in focus or not. So that'll be 12.5. That looks a little bit better. It'll be 6.25. It'll be 3.125. Let's take a look at our first finite differences. So our first finite differences are going to be 25 minus 50. And that's going to give us minus 25. 12.5 minus 25. And that's going to give us, oh, I better check. That'll give you negative 12.5, won't it? I think so, negative 12.5. Then we're going to have 6.25, take away 12.5, and that'll be 6.25, take away 12.5, negative 6.25. And then finally, you're going to have 3.125 subtract 6.25. So I think that's going to be negative 3.125. What do you notice? First ones are not constant. So therefore, not linear. Let's take a look at our second differences. So it's going to be negative 12.5. Now, it's negative 12.5 subtract 25. Negative 25. So the negative and negative give me a positive, and that'll give me 12.5. It's negative 6.25 subtract negative 12.5. So it's going to be positive 6.25. And then it's going to be negative 3.125 subtract negative, so that'll be positive. And that'll be positive 3.125. Okay, what do you notice? They are not constant. So therefore, it is not quadratic. Yay! But we can do better than that. We can look at what there is going on here. What is the pattern? And we're going to notice that there is a ratio here. There's a common ratio is present. Let's take a look at that common ratio. And we can take a look at it anywhere that we want. So it's going to be, let's do it from this to this one. So it's going to be 3.125 divided by 6.25. And you're going to find that that ratio is 1/2. And this one would be 6.25 divided by 12.5, which again is 1/2. We could have looked at that here. Negative 12.5. Now the negatives are going to bother you. Okay, we got some. You got negative 12.5 divided by negative 25. Don't get hung up. The negatives will, the negative on top and the negative on bottom will reduce each other out. So it's 12.5 over 25, which is 1/2. The same would happen here and here and here. The easiest place to look at the common ratio, though, is right here. Is right in your first y values, your range. So it's going to be 25 divided by 50, which is 1/2. Oh, you can't see what I'm writing. Haha. So let's come up here. So the easiest place is to see it here. So it's 25 over 50, which is 1/2, or 1.25, or sorry, 12.5 divided by 25, which again is 1/2, or 6.25 divided by 12.5, which again is 1/2. And we've got the common ratio happening all the way down here. So what's happening is, to go from here to here, you're timesing by 1/2. To go from here to here, you're timesing by 1/2. This is your common ratio. Okay? And so in terms of exponential growth or decay, that means that your base is equal to 1/2. That's the part that keeps changing. Okay, so that's going to be your exponential equation. Now in this case, we started with 50 grams, so we've got to take that into account, but that's your general idea. This whole thing has a half-life. Now, you've heard of half-life in chemistry. The reason why they call it a half-life is because the base is 1/2. Now, some substances have a third life, or a quarter life, or a fifth life, but this one happens to be a half-life. Looking back over here to the exponential ones, do you see how they kept going up by 3? This was tripling time. So the general equation for that is your common ratio is 3, which means that your base equals 3. So in terms of this exponential growth, it's going to be y equals, did I use y equals? I didn't. I said y equals 3 to the x, where this is your tripling time. Okay? Or your tripling effect. Let's see. Half-life, there you go. I need to get rid of this equal sign. So the base is 1/2, but once you take it up to the x, then that's actually how it's growing. So let's take a look at what we need to do down here. Write an equation to model the decay of plutonium. So look at, we know that it's decay. So what we can say, what we use for amount is mass. So we're going to use m as our function. So it's going to be mass. and we're going to say that the mass of it is going to equal, now we know that it is a half-life, so it's 1/2. Now we can put it up here in terms of H for its half-life, and it's going to be starting with 50 milligrams. Now, you've got to be careful. Where H equals a half-life. If you want, you could do mass will equal 50, 1/2, and you would have 24 years. See, this is getting tricky. So in this terms, if this is the half-life, it would be 1, 2, 3. But if you're going to do it in terms of years, so D would be total number of days, or total number of years, sorry. And this gets tricky because now, if you're going by years, so it would be 24 years. So it would be 24 divided by 24 is 1, so that's 1 half-life. Notice if it was 48 years, you'd put 48 up here. 48 divided by 24 is 2, so that's 2 half-lives. So you're going to take the half twice. 72, if I put 72 in for D, you divide it by 24. 72 divided by 24 is 3, meaning that you take your 50 and you divide it by 2 for the first half-life. You divide it by 2 again for your second half-life. You divide it by 2 again for your third half-life. So that's how that works. So we've got to be careful of that. If I'm just giving you the number of half-lives, it's easy. We just put in 1, 2, 3, or 4. But if they give it to us in terms of a number of years or a number of days, we've got to take that into account. So actually, what the formula is going to look like sometimes, I believe they're going to use time versus your half-life time. So in this case, had it been 72 years divided your half-life of 24 years, that gives you the 3, so that you're going to be taking the 1/2, the 1/2, the 1/2, or sorry, the 1/2, the 1/2, the 1/2 to get here. Assuming this trend continues, predict what amount would remain after 60 years. Okay, so there you go. That's the interesting part. You've got 60 years. So the question is, how many half-lives? So we want to know how many half-lives is that? Well, we know that a half-life becomes every 24 years, so it's going to be 60 divided by 24. So that's going to be 2.5 half-lives, so 2.5. So because I know the number of half-lives, I'm going to use this formula. So the mass remaining is going to be, we started with 50. We're going to have it have a half-life for 2.5 half-lives. So using your calculator, 1/2. Now, it's going to help you to know that that's 0.5. So 0.5 to the exponent, 2.5 equals times 50, means that I can be left with approximately 8.838 ... milligrams, and we'll take that to approximately 8.8 milligrams remaining. Now if I used this other formula over here, I'll do it with a different color. I could have easily said mass equals 50, half-life, and done time divided by half-life, and just done this work in the formula. So the mass would equal 50, 1/2. The time that went by was 60 years, and the half-life is 24. So you would do this work first. You got to do the exponent first, and then you're right back where we were when we had this. And you'd work that out, and it's going to be 8.8 milligrams approximately. Okay, so that's page 129 and page 130, and then I'll do the next page in the next video. Okay, guys.